galaxies main sequence, and those with low star formation rate is called passive galaxies. And sometimes we use delta ms to discuss about the offset from the main sequence along the star formation rate axis. So delta ms is calculated with this formula. But we now know that this relation comes from the more tight relation between molecular gas or whole gas and star formation rate, which is shown here, so-called Kennigan-Schmidt relation. So we know that galaxies with more molecular gas form stars more actively, but there is still some scatters here. And galaxies with alpha lift have a higher star formation efficiency. Star formation efficiency can be calculated in this way. And those in this bottom right corner have a lower star formation efficiency. And also, if we plot delta ms on the x-axis and gas fraction and depletion timescale. Depletion timescale is the inverse of star formation efficiency. We found that it is known that galaxies with elevated star formation have more gas compared to the low star formation galaxies. And also, they also have elevated star formation efficiency or shorter depletion timescale compared to these inner passive galaxies. So this is a relation. This is kind of relation for normal field galaxies. And how about cluster field? Oh no. Sorry. Yes. Yeah. So this is a stellar mass star formation relation for field or cluster galaxies. So these are combined, and we can see star formation in sequence and passive galaxies. If you only look at the cluster galaxies, you notice that passive galaxy fraction become higher compared to the field galaxies. So one of the key questions of my talk, my study, is to know which one is more important, gas fraction or star formation efficiency, to suppress star formation in clusters. In normal field, we know that both gas fraction and star formation play important role. But how about cluster galaxies? And next, another important question is quenching process. And there are many quenching process proposed in a cluster, acting in cluster environment. But let me classify only based on time scale. So like star formation depletion timescale is known to be around 1 giga-year, few giga-year. So shorter, fast quenching means quenching acting shorter than the depletion timescale. And like ground pressure stripping or tidal interaction stripping, which acts in like a few hundreds megayears. And for slow quenching, like strangulation starvation, which is a process mainly acting on halo gas of the galaxy. So they clusters strip the halo gas from the galaxy. So galaxy just forming star in a kind of close-box fashion. So it takes a relatively long time scale. And to distinguish fast or slow process, one way is see the gas component of the galaxy. And H1 gas is a very good tracer of environmental impact because atomic gas, normally molecular gas, distribute within a stellar disk, but atomic gas extend out to the stellar disk, like several times the stellar disk, where the gravitational potential not that high. So the atomic gas is more easily affected by the environment compared to molecular gas. This is H1 gas in control, overlaid on an optical image of one of a galaxy in Corona cluster, I think. As Bianca already showed a very beautiful jellyfish galaxies image, but this is one of the example of the round pressure galaxies. And plot here shows the delta. It's like delta MS versus delta gas fraction. And normal galaxies are shown in this grayish color, background grayish color, like contour. And coma clusters, it's shown in this color circle. They found that coma cluster galaxies deviate from the field relation toward the left upper side. And they consider some models, fast long time scale stripping, and they found that the deviation from this field relation is related to the time scale of the gas stripping. So fast gas stripping, indicated here, has a stronger impact on this difference in the location on this plot. And another way to distinguish the dominant quenching process, Bianca already mentioned this phase space diagram. So phase space diagram is like this. On a horizontal axis, we plot the distance from the cluster center, normalized by the typical cluster size. And on y-axis, we plot the relative velocity, normalized by the velocity dispersion of the cluster. And once the galaxy fall into the cluster, they make some kind of zigzag trajectory on this plot, and spiraling down into the cluster center. So recent inflows tend to locate alpha right area, and ancient inflow tend to locate lower left corner. But at the same time, if there is ICM, round pressure stripping, since round pressure stripping is proportional to the ISM density as well as the velocity of the galaxy, galaxies located alpha left corner are strongly affected by round pressure. So this right-hand side show the H1 observation of one of the cluster, and they show the H1 detection, non-detection on PSD. And they found that not only the ancient inflow, but also this round pressure area, galaxy located in this area also has showed some H1 deficiency. So this is one of the examples showing that round pressure stripping is playing a major role in reducing H1 gas content in galaxies. But in order to know the star formation, we need to know the molecular gas, since stars are known to form from molecular forming galaxies in local universe. So first, key questions we have is three. First one is which is more important for star formation quenching in galaxy cluster, H1 gas fraction or star formation efficiency from molecular gas. Second one is what causes star formation pointing galaxy clusters. So we use this delta MS and delta gas fraction relation, PSE, to distinguish which distinct dominant quenching processes. And we want to know the difference or similarity between different clusters. So we focus on the nearby galaxy cluster like Virgo and Fauna. So this is a comparison of our sample clusters. I also, not only Virgo and Fauna, I also put ASIAA for reference. I compare these three clusters, but please think this data is kind of a reference because this data comes from different CO transition for molecular gas mass estimate, and also they use a different IMF to estimate star formation and stellar mass. Anyway, these three clusters have relatively similar mass, 10 to 14, but Virgo is a little bit, has a little bit higher masses. So this is location of these three clusters. So we are here, local group, and Virgo cluster is here, and Fauna cluster is here, and here. And for those who are not familiar with ALMA, we also use archival data for Virgo cluster, but we got CO data for Fauna cluster using ALMA. So ALMA stands for ALMA Large Millimeter Centimeter Array, and it consists of main array, 16 4 12 meter antenna, and Atacama compact array or Morita array, which consists of 12 2-meter telescope and 4 12-meter telescope. And they can observe, we can observe with ALMA in frequency range of from 35 gigahertz to 950 gigahertz. And for your reference, nowadays the number of nearby clusters with CO observation is increasing. Like Virgo in the vertical project, and Phonax, and Eridanus not cluster but supergroup, and Hydra and their comma. So in coming years, I think we will know the variation of the molecular gas properties in the different clusters. And the key quantity in this study is star formation rate and gas mass fraction and star formation efficiency. And we compare the field and different cluster galaxies. And we judge whether they are different or not based on a p-value of the two-sample case test. If the p-value is less than 0.05, we consider these two samples are different. And before the comparison, we remove the stellar mass dependence of these key quantities, and like delta MS, we fit the stellar mass dependence of these quantities and remove it before the comparison. So this is the comparison of star formation rate and gas mass fraction and star formation efficiency. And if we focus on the median value of this field of Virgo, Fauna, and the cluster, we found that as expected, cluster galaxy have reduced star formation rates. And so if the difference is statistically meaningful, I use this one. And if the p-value is larger than 0.05, I use this And so star formation rate is this one. And for gas mass fraction, we find the same tendency as we found in star formation rate. So, but we didn't find clear difference among few or different clusters. So galaxy clusters with higher star formation rate has more gas, but the star formation efficiency is not so different. So this plot shows the black shows Virgo, and green shows Ponax, and ASIAA is shown in purple, and field is supposed to be delta field 0. And so next, delta MS and delta gas fraction or delta star formation efficiency. The field, I plot the field galaxies in contour in background, and we plot the Virgo Ponax ASIAA in this color or symbol. And we found that cluster galaxies tend to have lower gas fraction compared to field galaxies, or elevated star formation efficiency compared to the field relation, or for fixed delta MS. So to check more quantitatively, we divide the sample into main sequence and passive sequence, and check whether these star formation rate or gas fraction or star formation efficiency are different or not. And as expected, we found that gas fraction in cluster galaxies are lower than the field galaxies, but star formation efficiency doesn't change much. But if you look at this passive population in Virgo cluster, we find slightly higher star formation efficiency. So this indicates that molecular gas in Virgo is maybe also molecular gas in Virgo. It can be affected by some fast quenching process. Next, this is a comparison between star formation or gas component with the accretion phase, which is the y and the x-axis of the phase diagram. So then symbol shows black symbol shows Virgo, and green shows Ponax, and purple shows ASIAA. And this is the accretion phase, and smaller value indicate ancient inflows, and larger value indicate recent inflows. As you can see that there is this kind of trend in Virgo and Ponax. Like ancient inflows tend to have lower star formation rates and lower gas mass fraction. But star formation efficiency, there's no clear difference. But another important result is that Virgo cluster has a shallower slope compared to Ponax cluster, which may indicate the run pressure stripping play a more important role in molecular gas in Virgo cluster galaxies than Ponax cluster galaxies. So summary, so the key question, main goal of this study is to understand the quenching mechanism in cluster galaxies. So since the stars are formed in molecular gas, we compare the molecular gas properties of field in two different cluster galaxies. And we found that low star formation activity in Virgo and Ponax galaxies is mainly attributed to low gas mass fraction rather than star formation efficiency decreases. And also different clusters may have different dominant quenching processes. Like Virgo has more, in Virgo cluster, run pressure stripping have a more impact compared to different ones. This is also indicated from the X-ray observation of ICM in Virgo Ponax, since Ponax has a stronger X-ray emission, so they might have more dense ICM compared to Ponax, or dense and standard ICM. And for future works, third, for future works, I want to do one spatially result. I want to check the spatial results of properties. So we conducted a CEO survey to our normal field galaxies, more than 100 galaxies. And we found that galaxies with low delta MS tend to have reduced gas fraction near the galaxy center. So this is a gas fraction as a function of distance from the galaxy center. And also, those with this low delta MS tend to have low subformation efficiency at the disk region. So I want to check this kind of thing in our cluster galaxies. And also, recent study shows that preprocessing in filament has non-negligible impact on the subformation activity. So, like the previous study already shown that H1 gas is floor for less massive galaxies nearer to the filament spine. So I want to see whether that kind of difference can be seen also in molecular gas or not. But at that time, it is important to pay attention to backsplash galaxies, since so this is the fraction of galaxies as a function of distance to the central halo, and one corresponds to R to 100. So but around R 200, like 60% of the galaxies are expected to be backsplash galaxies. So we need to pay attention to this effect of this backsplash galaxy. So we may need to consider more outskirt galaxies, outskirt filament galaxies to see this effect. Thank you.
We have time for a couple of questions. And by the way, if you are not in Slack yet, please email me or email Julie. So, questions? So I'm curious. So how would you identify splashback galaxies?
That's very difficult. So some maybe phase diagram can be used. Your study suggests that backsplash galaxies are likely to be located like this area. Relatively larger X but smaller Y. No, kind of statistical way, yeah.
Are there any questions? If not, then let's thank Dana again.